Hello. In the last video, we discussed what is disjoint set union or union find. Let's discuss some standard questions and some code modifications. And let's say we have to find the number of components or connected components in a graph. How can we do this? We can simply start using BFS or DFS. So for every node from 0 to n minus 1 or n, we will find whether it is visited or not. And if it is not visited, then we will try to start visit all the nodes that are reachable from this node, and we will try to make sure that we will make those visited. For example, this is the graph and we will start from this node. Is this visited? Because initially we have all the nodes are unvisited, so we'll start from 0. So this is unvisited initially, so we'll make this visited and we will try to do BFS on this, and we'll try to make sure all the nodes that are attached to this or that are reachable from this as visited. So this is we will reach one, we will reach this node and we'll make this visited, and similarly one. And if there are many other nodes in component, then we'll make all this one. And similarly, after coming to the next node, if this is the next node, for example this is 0, this is 1 and this is 2. So obviously if we come to 1, it is already visited by some previous node. It means that it is already connected, so no need to start BFS again from this, and similarly from 2 again. And this is 3, so 3 is unvisited because we did not reach this vertex from any of the previous vertices. So visit this and start BFS from this and mark all those vertices in this component. So in this way we can find the answer of BFS. But what if we want to do in some other method, not from BFS or DFS? So what is the main thing here? Because we have to count only once the every current component. So the component 1 should be counted only once, and component 2 also should be counted only once, and similarly any other components which are existing. So any component should be counted only once. So what if instead of trying of all nodes, what if we have only single node? Obviously if we have n single nodes and if we make sure that they all are single, that means there are no connected edges between them. So answer is n simply, because if there are n and if every component has only one node, and it means that there are no connected edges, so it means that they all are independent, and the answer is n connected components with each connected component as only one node. So the main idea boiled down to representing the whole component into single one, because it will be very easy to find the count of components if this is the case. So this is where exactly DSU comes in. DSU helps to boil down a single connected component to single value. So in the before video we discussed what is find and merge functions. So we can store ultimate parent nodes of every node in the parent component, in the parent vector. So after merging the nodes or edges using DSU, then how can we find the components? We discussed that we are trying to represent the whole component in a single node. So what is the unique number for every component in a DSU? It is a parent node. So after storing the edges in DSU, we will traverse every node and we will try to store the values in a set. Store the ultimate parent node of every node in the set. So after that, we will try to return the size of set, because for every connected component, the values are same, because the parent of this will be this itself, and parent of this node will be 0, and parent of this will be 0. And similarly, if we try to store in DSU, for every connected component, the node of the parent of every node in that component will be the ultimate parent. So we are trying to represent the whole connected component with a single value. So in this way, after storing in DSU, we can traverse all nodes and we can find whether we can store the parent of that in set, and finally we can return the size of set. So this is the initial DSU. The parent of every node is that node itself. Initially parent of 1 is 1, parent of 2 is 2, and so on. Because initially all are disconnected, and now we are joining 1 2. So they are in different connected components. So join these two, and similarly join 1 3, and similarly join 4 5 and 3 6 and 2 6. So after completion of edges, then we will start traversing every node. So the parent of 1 is 1 itself. So we'll add 1 in the set, and parent of 3 is also 1. So add that in the set as well. And similarly parent of 2 is also 1. Parent of 6 is also 1. Parent of 4 is 4. Parent of 5 is 4. And parent of 7 is 7 itself. So as we are storing in set, all these will be counted only once. So finally the size set will be 3 and the answer is 3 because we are representing a whole with respect to only one with respect to node 1, and similarly we are representing 4 5 with respect to only 4, and similarly with respect to 7 we are only considering 7. So in this way we can try to use GSU and find the number of connected components in the graph. Let's come to next one. So how to find whether there is a cycle in unrelated graph or not? We can use BFS or DFS, and let's simulate using BFS and try to think of some other way. So initially 1 and 2, we will add the edge between 1 and 2. Let's assume initially all are unconnected. So 1, 2, 3, 4 all are disconnected initially. And now we are gradually adding the edges. So after adding 1, 2, this is the new graph. After adding 2, 3, this is the new graph. After adding 1, 4, this will be the new one. And now coming to 3, 4. So before adding 3, 4, let's say we have added 3, 4. So after adding 3, 4, when there will be a cycle formed, there will be a cycle formed initially if there is a component like if the nodes 3 4 are already previously connected, because without 4, without adding this edge, the graph does not have a cycle because we are reaching this node because we are traversing from initial edge. For example, if we found the cycle here, we'll just return from this one. We will not traverse this. We will not traverse the before edges, below edges. But now, so if we are reaching an edge 3 4, it means that there is no cycle till the previous edges. So it means that there is no cycle form. So this is the before graph form before adding 3 4 edge. But now when we are trying to add 3 4, it forms a cycle only when already 3 4 are connected. So the question now boiled down to find whether nodes 3 4 are in same connected component or not. If they are in the same component, it means that if we add an edge, then it is a redundancy edge and there is a cycle form. And if they are not in the same connected component, it means that we are adding a new edge and there is no cycle form. So the ultimate question reduced to find whether two nodes are in the same connected component or not in OF1, because we cannot do BFS or DFS for every query and for every edge, and we cannot find whether they are connected or not. So we have to find the answer in OF1. So exactly this is also a case where DSU comes in. So we can store the nodes in DSU, and for every edge before merging the edge, we can find whether they are both in the same connected component or not. If they are in the same component, then return true because we found a cycle. And if they are not connected, then simply merge or add the edges. So initially 1 2. So initially every node is a parent of itself. So adding 1 2, adding 1 3, adding 2 3, and adding 1 4. And before adding 3 4, we will check whether ultimate parents of 3 and 4 are equal. So ultimate parent of 3 is 1, and ultimate parent of 4 is also 1. So ultimate parent of these both are equal. It means that they are already in same component. So no need to add any edge, return 1 because we found a cycle. So in this way we can solve some very basic questions using DSC also. And what are the some code modifications? So in the before video we discussed some codes of find and merge, and there are some many ways or many requirements where we have to modify the code. So in some cases we may have to return true if they're already connected, and in some cases we may have to return true if we merge nodes in the operation. It means that they are not connected before. For example, there may be a requirement return 1 if they are already connected. For example, we are adding edge JB now, and in some cases there is maybe a case where we have to return true if they are already in the same connected component, or in some cases there may be requirement where we may have to return 1 if they are not connected. So we have to make sure we have to make changes in code before trying DSU. And similarly, coming to the next case, for example, we want two DSUs. So what if we want two DSUs? We cannot create two parent vectors or two size vectors for initial two DSUs. So instead of doing this, we can try to create a class with a parent and size attributes, and we can use two objects for two DSUs. So for example, we have to construct two DSUs. We cannot create two parent vectors or two size vectors, and we can do computation because what if we want three DSUs or many? So in that cases, we can try to create a class for DSU, and then we can try to create two DSU objects, and we can access parent 1 and size 1 from first object, parent 2 size 2 vector from second object. So this may be also a case which may be useful. And coming to next one. So in the before video, we checked the code of function merge. So there may be a case where we have to add additional functionalities also using the parent and size vectors. So we have to be flexible in making the changes in code, and these are some basic kind of modifications that we make. So just instead of remembering or using a template, we have to check whether there are some modifications or not, whether it is better to use DSC or not, and whether there are any better additional functionalities that are useful for the present question. And now from the next videos, I will try to start some new questions. So make sure to do some easy questions on DSU, like some connected components or cycles or some other basic questions. If you have a doubt, comment below. See you in the next video.